A gas turbine and generator working together are officially known as a gas turboset. This system has two main modes: single cycle, where it delivers electric power directly to the grid, and combined cycle, where the exhaust gases are sent to a heat recovery steam generator, HRSG, to squeeze out even more efficiency. To understand how this works, we need to look at its major organs: the air intake, compressor, combustor, turbine, exhaust system, generator, and exciter. The air intake system is responsible for capturing ambient air and processing it through a series of filtration and acoustic damping stages. Once treated, this air is directed into the combustor, where it fulfills two vital roles: supporting the combustion process and providing necessary cooling for high-temperature components. Louvers. Serving as the primary intake point, louvers are engineered to draw in atmospheric air while acting as a physical barrier against rain and large debris. Filtration system. The air is purified by a standard two-stage filter that captures dust, dirt, and other airborne particulates. In more challenging environments, a three-stage filter may be utilized, while pulse-type filters are available as an optional upgrade for self-cleaning capabilities. Silencer. As the air reaches high velocities, it passes through a sound-damping silencer. This component is essential for reducing the aerodynamic noise generated by the intake flow to acceptable levels. Safety flap valves. Positioned downstream of the filter housing, these valves serve as a critical fail-safe. If filters become obstructed and internal negative pressure exceeds safe limits, the valves trigger automatically. This bypass prevents structural deformation or damage to the filter housing, manifold, and intake elbow. Anti-icing device. For units operating in frigid climates, an anti-icing system is integrated to inhibit ice accumulation at the compressor inlet, ensuring uninterrupted airflow and protecting the compressor blades. Manhole. A dedicated access manhole is integrated into the ducting, allowing for routine maintenance, internal cleaning, and technical inspections. The compressor receives airflow from the intake system, significantly increasing its pressure through the synchronized action of rotating blades and stationary vanes. Upon reaching the compressor outlet, the air is channeled through a diffuser into the combustion chamber. From there, a portion is utilized within the hot gas path for essential cooling. Additionally, a specific volume of compressed air is diverted to provide critical sealing at points where the rotor penetrates the casing. Positioned at the cool end of the gas turboset and coupled to the compressor rotor, the intermediate shaft serves as a vital mechanical link with four primary functions. Power transmission. It transfers mechanical energy from the gas turbine rotor to the generator. This torque is transmitted via frictional forces established by pre-stressed coupling bolts within the flanges. Thermal protection. Barring. During the cool-down phase following a shutdown, the shaft transfers slow rotation motion from the barring device through a latch wheel. This prevents the turbine shaft from bowing or bending due to uneven thermal contraction. Speed monitoring. Utilizing an integrated gear wheel and phase angle transmitter, the shaft facilitates non-contact measurement of the rotor's actual rotational speed for the control system. Phase angle tracking. It enables precise phase angle data to be relayed to the control system via non-contact proximeter measurements. The compressor is housed within a rigid, axially split casing made of globular cast iron. This split design allows for streamlined maintenance and internal access. The unit is bolted into a single, robust structure and is supported by a base plate at two specific points per support. To maintain alignment, it is fixed axially within the intake manifold section. The rotor serves as the mounting point for the rotating blades, which are secured in precision machined grooves. Engineered as a single, stiff shaft made of welded discs, the rotor offers several distinct advantages. Integrated sealing. Grooves are included to hold sealing strips for both cooling and sealing air. Ease of balancing. Balancing weights can be added through dedicated holes without requiring the disassembly of the machine. Reliability. The welded construction is virtually maintenance-free and is supported by journal and thrust bearings, with axial fixation established in the air intake manifold. Located in a single row at the casing inlet, the variable inlet guide vanes regulate the volume of air entering the compressor. These vanes transition between open and closed positions via commands from the automated turbine controller, ensuring optimal airflow modulation across various operating conditions. To maintain aerodynamic stability during gas turbine startup and shutdown sequences, the system utilizes blow-off valves. These valves expel surplus air into the atmosphere, effectively preventing air turbulence within the compressor. This regulation is critical to avoid unnecessary mechanical stress on the compressor blades. Strategically positioned along the casing, the valves are operated by a specialized hydropneumatic system, which is managed directly by the EGATROL turbine controller. Located at the compressor outlet, the diffuser is a precision-engineered, ring-shaped component. As compressed air exits the diffuser, it is redirected by guide vanes into the turbine housing. This airflow performs a vital thermal management function, cooling the turbine's stationary vane carrier before it is ultimately funneled into the combustor for ignition. The compression of intake air is achieved through the coordinated action of rotating blades and stationary vanes, fixed blades. The design of this assembly focuses on durability and precise alignment. Spacing and alignment. To maintain exact aerodynamic spacing, the blades and vanes are kept apart by dedicated intermediate pieces. Security. To ensure the rotating elements remain secure within their machined grooves, the blade roots are fastened with robust locking pieces, preventing any risk of displacement during high-speed operation. Material composition. The blading is engineered for high performance without the need for internal cooling. Each blade and vane is manufactured as a single, solid piece, either cast or forged, from a high-strength chrome steel alloy, providing superior resistance to the stresses of the compression cycle. Located within the air intake section, the compressor's rotor is precisely supported by a dual bearing system consisting of a journal bearing for radial stability and a thrust bearing for axial positioning. These components are continuously lubricated and cooled by the centralized lube oil system, ensuring optimal thermal regulation and friction reduction during high-speed operation. Engineered for maximum accessibility, the bearings feature a horizontal split shell design at the rotor's axis, allowing for comprehensive inspection, repair, or replacement without the need to disassemble the main compressor housing. To ensure long-term mechanical integrity, each bearing is integrated with dedicated sensors that provide real-time monitoring of vibration levels and oil temperatures, allowing the control system to detect potential issues before they impact performance. The combustor is a ring-shaped, annular chamber positioned around the shaft, bridging the space between the compressor and the turbine where the ignition process occurs. This stage facilitates a chemical reaction between oxygen from the compressed air and the carbon and hydrogen components found within the fuel. Once this mixture ignites inside the combustor, the resulting high-temperature, high-pressure gas is channeled into the turbine to be expanded across the rotor blading. This system is designed to burn either gaseous or liquid fuels, which are precisely supplied to the chamber by the dedicated fuel delivery system. To manage the intense thermal energy generated during the combustion process, the combustor relies on a continuous supply of cooling air diverted from the compressor. This thermal regulation is achieved through a counter-flow arrangement, where the internal flow of hot combustion gases and the external stream of cooling air travel in opposite directions to maximize heat dissipation efficiency. The primary structure of the annular combustor consists of a ring-shaped housing that secures and integrates all internal combustion components. This assembly is suspended within the main turbine housing, strategically positioned between the compressor and turbine sections. To facilitate streamlined maintenance, the outer turbine housing features a horizontal split shell design, allowing the combustor to be easily accessed. Furthermore, an integrated manhole is provided to ensure that routine inspections and servicing can be conducted quickly and efficiently. The initial combustion stage is centered within the front segment and its corresponding support structure. This assembly features a specialized cover plate that serves a dual purpose. It provides a secure mounting point for the burners and incorporates precision-drilled apertures. These holes allow pressurized combustion air from the compressor to transition into the burners, ensuring a consistent and controlled environment for the ignition process. To safeguard the primary combustion zone from the intense effects of direct flame radiation, a heat shield segment and its corresponding support are integrated into the assembly. This shielding is further reinforced by an active cooling mechanism, where pressurized air from the compressor continuously circulates across its backside to manage surface temperatures and ensure long-term structural durability. The combustor features 72 double-cone EV burners organized in a dual-row annular pattern. This specific arrangement is designed to facilitate a thorough blending of fuel and air, ensuring a stable and continuous combustion process while maintaining a compact combustor profile. Each burner is engineered as an axially divided hollow cone, with the two halves offset to create longitudinal slots. This geometry serves several critical functions. Air intake. Combustion air enters the burner through these slots, initiating the mixing process. Vortex generation. The offset design induces a powerful swirl flow, creating a central backflow zone. Ignition stability. Within this backflow area, flow velocities are reduced sufficiently to allow for reliable ignition. This prevents the flame from being blown out by high-velocity air. The EV burners are optimized for lean combustion, which provides several operational benefits. Low emissions. The lean fuel-air mixture maintains lower flame temperatures, significantly reducing the production of nitrogen oxides, NOx. Mechanical integrity. Lower temperatures and stable flame patterns minimize combustor vibrations and eliminate flashback risks, where the flame travels backward into the burner. Dual fuel capability. For liquid fuel operation, an atomizer nozzle integrated into the burner head sprays fuel into the vortex. To meet strict emission standards during oil combustion, water is injected via a dedicated nozzle in each burner to further suppress NOx formation. To manage varying load requirements and power changes, the burners are controlled in groups, allowing them to be staged, switched on or off, as needed. This modular approach ensures high efficiency and flame stability across the turbine's entire operating range. A turbine transition piece effectively channels high-temperature combustion gases into the turbine stage while ensuring minimal thermal energy loss. Constructed from advanced heat-resistant plating, this component is formally identified as the secondary zone, Zone 2. To maintain structural integrity under extreme operating conditions, the transition piece is continuously cooled by pressurized air supplied from the compressor. Two electric igniters trigger the ignition torches, which utilize fuel gas or propane delivered from the ignition gas system. Once the main burners receive fuel, the flame propagates from one burner to the next without requiring additional intervention. After stable combustion is confirmed, the igniters are immediately deactivated. The entire sequence for activating and disabling the fuel ignition system is managed by the automated turbine controller. Combustion monitoring is performed by 3 flame sensors operating under the turbine controller's command. Their data is processed through a 2 out of 3 logic circuit, ensuring the gas turboset stays active as long as a minimum of 2 sensors detect a flame. Should the system fail to meet this threshold, the turboset is immediately tripped. This redundancy prevents accidental shutdowns while maintaining high safety standards. In today's video, we've taken a deep dive into the air intake system, the compressor, and the combustor. In our next installment, we'll be shifting our focus to the remaining major components of the gas turboset: the turbine, the exhaust gas fixture, the generator, and the exciter. Don't forget to like and follow so you don't miss out on the next chapter of this series. Thanks for watching, and we'll see you in the next one.